a brand new Lambo.
Hi everybody. So in this video we are going to look at sketching polynomial functions and how we can use a sketch of a polynomial function to solve a polynomial inequality. So a polynomial function is anything of the form with x to the powers and coefficients combining those terms, an example of which is given here. So if I want to sketch this function, the first thing I'm going to do is try to figure out what it's doing in its end behavior. The second thing I'm going to do is kind of look at what it's doing in between those ends to kind of get a picture of what how it's behaving. So to figure out the end behavior, we use something called the leading coefficient test. The leading coefficient test is based off of really just the first term when it's written in standard form. And we're going to look at the coefficient of that first term and also the power of that first term. So based off of the power, if the power is even or odd, that's what I'm going to use to distinguish between two conditions. And then the other component is the term itself, if that term is positive or negative. So if it is an odd degree polynomial with a positive leading coefficient, I'm going to fall to the left and rise to the right. If it is a negative leading coefficient of an odd polynomial, it's the opposite of this, rising to the left and falling to the right. We could do similar inference if my degree is even and my leading coefficient is positive, I rise left and rise right. And if my leading coefficient is negative on an even polynomial, I fall left and fall right. So if I'm looking at this polynomial, I have a negative leading coefficient and it is of odd degree. So I have a negative odd. Negative odd tells me odd, negative, that I am going to rise left and fall right at the ends of my polynomial. Great. So if I go to make a sketch with this polynomial, because it's negative odd, I know that it's rising to this side and falling to this side. Now what I have to do is kind of figure out what happens in between. So to do that, we use the roots and a concept called multiplicity. When I have repeated roots of a polynomial, we say that that root has multiplicity, meaning it occurs multiple times. Any factor of a polynomial function which has degree greater than 1 yields what we call a root of multiplicity k. So if something appears 3 times as a factor, it has multiplicity 3. Knowing the multiplicity of a root helps me to determine the behavior of that root around, or behavior of the function around that root. In general, if we have odd multiplicity, it will pass through the axis. Like if I have a multiplicity of 1 or a multiplicity of 3. And if I have an even multiplicity, it will lie tangent to the axis or bounce off. So let's apply this concept to our example. So before I can use the multiplicity concept, I have to first find the roots. And I can do that by factoring. So if I rewrite this polynomial function in its factored form by first factoring out the common factor of negative x, and then noticing that what remains happens to be a perfect square, I could then find the roots by looking at where the y value is 0. That is because y is 0 all on the x-axis, which will give me the location of the roots. So once I have that, I can see that either x equals 0 or x equals 2 are my roots, and because x minus 2 is squared, it's going to have multiplicity 2. So to use this concept when graphing the function, I'm going to plot x equals 0 and x equals 2 as my roots. So this is the point 0, 0 and the point 2, 0. So with those and noting their multiplicities, since my function starts from above, it's going to come down and it's going to have to, I'm actually going to shift it over a bit so I get a kind of cleaner image. My function is going to come down and has to pass through that point 0, 0. I know it passes through because it has multiplicity of 1, which is an odd value, so it passes through the root. Then to get back to this root, the graph will have to turn around at some point, come back, and because this root has multiplicity 2, it will lie tangent. So it's going to bounce off that root and will not pass through the graph. Then based off the end behavior, it will continue to fall to the right. So that's what that rise left, fall right means. Rising to the left, falling to the right, passing through odd multiplicity roots, bouncing off even multiplicity roots. That gives me a nice sketch of my polynomial function. So one application of graphing polynomial functions can actually be used to help us solve polynomial inequalities. So suppose I have an inequality like the one on the left. What I need to do to solve this inequality is locate the critical values. This is the x-coordinate of the function, which makes the y-coordinate 0 or undefined. So to locate this, what I'm going to do is I'm going to define the polynomial function y equals 2x cubed minus 5x squared minus 14x plus 35. Now, if I'm defining y that way, that makes this entire left-hand side of this inequality the y value. So essentially, I need to find the x values that make the y values less than 0. To do that, that's where we're going to identify these critical points where it's equal to 0 or undefined. And then I can look around at the rest of the intervals to see which sections is the graph negative and which sections is the graph positive. This can be sped up very, very much if we just sketch the polynomial function. So I'm going to use the same procedure we just discussed. So I'm going to take this function and I'm going to find the roots. So by setting the y value equal to 0, get that critical value from the roots. And if you go through the factorization process, you get that x is 5/2 or plus or minus rad 7. So I'm going to use the sketching process to get a sense of, okay, where are the y values less than 0? By the leading coefficient test, I can look at the degree of my polynomial and the positive or negativeness of its leading coefficient. And since this has an odd degree and I have a positive leading coefficient, positive odd tells me this should fall left and rise right. So I know the end behavior, and then I can plot the roots. So 5/2 is about 2.5. So I'll get, I'll go 1, 2, 2.5 would be about there. And the square root of 7 is somewhere between 2 and 3 as well. It's a little bit bigger than 2.5. And if you're unsure about what the value is of rad 7, we can use a calculator to approximate that value to get a sense of where on the number line it falls. I'm just waiting for my calculator to open so that we can confirm that square root of 7 is in fact bigger than 2.5 at 2.64. Okay. So square root of 7 is going to be slightly to the right of 5/2. 5/2. I'll put it here, square root of 7. And then I also have negative the square root of 7, which is to the other side of my interval. Since none of these roots have any multiplicity, or you could think of it as multiplicity of 1, all of these roots will pass through the x-axis. So starting from the lower value, I'd come up to negative rad 7, pass through the axis, at some point turn around to come back to 5/2, pass through the axis, and then turn around to go back through the positive square root of 7, confirming that I'm falling to the left, rising to the right, and I only pass through the axis at a root. Once I have it sketched, this is the graph of x values along the horizontal and y values along the vertical, so I can see that the y values are less than 0 anywhere to the left of negative 7 or between 5/2 and rad 7. So the x values that make this y value negative would be any x value which falls on the interval negative infinity to negative the square root of 7, or on the interval from 5/2 to positive the square root of 7. And those are the intervals of x values for which the y values are negative. I've therefore solved for where on this polynomial inequality it will be negative. Okay, so that is it. Please continue to watch the review playlists, the review videos in the review playlist, so that you are prepared for the final exam. Take care, everybody.